In today's video, we will learn about latent heat and phase change. A phase change occurs when the physical characteristics of the substance change from one form to another. This involves a change in internal energy, but no change in temperature. So for example, when we have a solid structure of ice, the heat is transferred as energy that is used to change the structure of the substance, but doesn't increase the temperature of the substance. So we see that our solid structure of ice will be transformed into its liquid form of water, which will then be transformed from its liquid state into its gas state in the form of steam. Latent heat is the energy needed to change the phase of a given pure substance, and is given by the equation that Q, our energy, is equal to our mass times L, where L is called the latent heat of the substance, and it depends on the nature of the substance change as well as the substance. And this is expressed in the SI units of joules per kilogram. When a substance is being transformed from its solid to liquid state, or liquid to solid state, the latent heat we use is called the latent heat of fusion, which is the phase change that occurs during a melting or freezing. And we see that the latent fusion for water is equal to 3.3 times 10 to the fifth joules per kilogram. When our phase change occurs during a boiling or condensing, meaning we're going from a liquid state to a gas state, or a gas state back into its liquid state, the latent heat of vaporization for water is equal to 2.26 times 10 to the sixth power joules per kilogram. So the best way to summarize a phase change is by looking at a phase change diagram, which we have on the right. We see that from point A to point B, temperature is increasing, so we're having heat added into the system, although our phase is still in the solid phase. From B to C, we see that our temperature isn't increasing, however, we're going from a solid state into a liquid state. Once we're in our liquid state, additional energy is added, and we see that our temperature increases until it gets to its next phase change from its liquid state into its gas state. And during vaporization, we see that there is no change in temperature. And then from there on, our temperature can increase while it's in its gas state. And just how this reaction went to the right as energy was put into the system can also be reversed by reducing the energy in the system, where we can go from the gas phase back to its solid phase. So if we were given an example that asks us how much energy is needed to change a 40-gram ice cube of ice at 10 degrees Celsius to steam at 110 degrees Celsius. So the information we're given is that the mass of our ice block is equal to 40 grams, and that our initial temperature is a value of negative 10 degrees Celsius, and in the gas stage, its final temperature will be 110 degrees Celsius. So if we write an equation that shows the heat put into the system, we'll have Qs for our energy put into the solid of ice plus QL of F, which will be the energy needed to transfer our block from its solid state to its liquid state, plus Q of the energy put into its aqueous state, plus Q of LV, transforming it from its liquid state into its gas state, plus the energy that's put into the system once it's in its gas state. So we see in our equation we'll have 5 Qs. If we expand our equation, we see for our solid state we'll have our mass times our specific heat multiplied by our change in temperature, plus our mass times the latent heat of fusion, plus our mass of ice times our specific heat times our change in temperature plus our mass multiplied by our latent heat of vaporization plus our mass times our specific heat times our change in temperature. So now we can plug in our variables and solve for the total amount of energy needed to transform the ice into steam. So first we must convert our mass from grams into kilograms. We do so, we see that our mass will be equal to 0.04 kilograms times our specific heat of water, which is 4,186, multiplied by our change in temperature. We see that our change in temperature is initially from negative 10 degrees Celsius to 0 degrees Celsius. So we'll have a change of 10 degrees Celsius plus our mass of ice, once again, multiplied by the latent heat of fusion, which for water has a value of 3.33 times 10 to the fifth joules per kilogram plus our mass of ice, which is now in its liquid state, multiplied by specific heat of water, multiplied by its change in heat from 0 degrees initially to 100 degrees Celsius, which is a change of 100 degrees, plus our mass of water transforming into its gas state by our latent heat of vaporization, which is equal to 2.26 times 10 to the 6, plus our final mass of water multiplied by our specific heat of water multiplied by our change in temperature from 100 degrees to 110 degrees, which is a change of 10 degrees Celsius. So I ended up putting brackets around each of our Q's. So we see we still have 1, 2, 3, 4, 5 Q's. And now we can simplify our equation by calculating out each Q and then adding them together. So if we do that real quick, we see that our first Q had 1,674.4 joules of energy plus our second Q, which was equal to 13,320 joules. Our third Q, which was 16,774 joules plus 90,400 joules of energy for our fourth Q. And then finally, for our fifth Q, at a value of 1,674.4 joules of energy. And if we add this together, we see that our total amount of energy added into the system is equal to 123,812 joules, or we can rewrite this as 124 kilojoules of energy.